We've already seen that changing the our basis states in quantum mechanics is more or less like a generalized Fourier transform in some respects, anyway. But let's look at that in a little more detail from the formalism side of things. So I'm going to be changing a basis in quantum mechanics. Suppose that we have two complete orthonormal bases. Okay? I'm thinking one is a phi I. Here, these could be the energy eigenvalues, for instance, and over here another chi I, another complete basis, as these might be momentum, as just a for instance. And what we know is that they're both complete bases, and so I should be able to expand any state that I want to. And here I've got a general state psi that I can expand on this orthonormal basis set. It's just the sum over all the psi's, or all of the i's, and I get these expansion coefficients ci, basically the components and the phi on the phi basis. And again, this could be a continuous or it could be discrete. Here I've got it listed as discrete. If it's continuous, then I have to integrate over this. This would be a continuous variable here. And we know how to get the CIs. It's just the projection of the psi onto each one of these basis elements with this inner product. But I could also do the same thing, since I have another complete basis set here, the chi-i's. I could do a similar expression for the same state. I could say, well, no, I want to use momentum wave functions or basis sets, and so I get a different set of expansion coefficients. And but again, I can always get those if I know this basis set. I just take this inner product with the chi-i's to get the di's. And then the question is, can we find these expansion coefficients, ci or di, in terms of the other one? Here I pose it as, can we find the di's here in terms of the ci's? And well. These expansions hold in general, so I could certainly, and any one of the phi's is certainly in this class of general states. I could certainly do an expansion of it in terms of the chi-i's. And then, if you look at it, you've got a summation over all of these basis sets here. Summed over all j, that's over all of the chi bases, and I still have an index because I'm looking at a specific phi here, and so I have these expansion coefficients have a double index in it, and I just represented it by u, whatever this number happens to be. However, I know that the CI's are just the phi's into any state here, and so I've got this general expansion in terms of di's, and I can take the inner product of these di's with the phi's here to get this expression. It just comes across. This is summed over j, and it's phi chi j dj. And now that if you look at that, this becomes really a matrix here. I rewrite it in this form, summed over j, and then I get the CI. And so we have a direct relationship between the expansion coefficients here and the other. But these are just what I would call the phi j, or the uij's. And if I dot product this in with I, then or with j, or with another basis set, I get these. So altogether, one has a relation that is this U matrix summed over j to get these expansion coefficients. So in effect, we can change basis sets, and that doesn't affect any of the other states. The states are the same. We're just looking at their components in different ways, but we have this transformation to transform directly from their components. Now, in general, we choose orthonormal basis sets, and so these become delta IKs. And if you do this, we've got these the phi's is just this transformation ki, phi k here, summed over j. That's this one, and I do an expansion on this one. That's an I, and I summed over L here. Okay? And that's the Hermitian conjugate of this mess. And we know how to do that. It's just this becomes this ket vector becomes the bra vector, and then this matrix here I have to transpose it, so I have to switch the rows and columns and take the complex conjugate of it. And then I can bring both of these sums outside, and I get an expression that looks like this: jk uil, complex conjugate. And then I get a chi j chi l. But again, they're an orthonormal basis set, and so they become just this Kronecker delta. And so we get this expression here. If you look at this, this is in fact the Hermitian conjugate. I could switch these back again if you like, and but this is just the Hermitian conjugate of the original matrix, and so this turns into the matrix result that when I operate this, well, these are delta IK, KL is just this product here. Remember, these were this was an orthonormal basis, and so this is a delta KL. But that's just an identity matrix, and so we get that U dagger has to be equal to an identity matrix. And so the U must be a unitary operator that transforms from one basis set to another. Right? And it holds for any vectors that are in it, and particularly it holds for the basis vectors themselves, and that forces us to be these unitary operators. So any unitary operator is really just like you're changing the coordinate systems in regular vector problems. You're free to choose any coordinate system that you want, but you have to realize that with your choice of coordinate system, the components of any given vector may change, but the vector stays the same, and that forces you into some relationships between the components from one coordinate system to another. Same thing in quantum mechanics. The only difference is that the operators that do this have to be unitary.